Okay, so welcome back on the morning, second speaker of the morning session. I'm also super happy that introducing the Pedro Lopes, Associate Professor Pedro Lopes from the University of Chicago. So we know each other a very long time, and then we always kind of having a chat about like human augmentation, integrating computer and human, and then also he's now visiting the OIST in 2 or 3 months, the TSVP program, and then we have a very nice time. And then also like one thing, I made a very good contribution to the OIST, which is like I think it's the last year you, the Pedro, visited here, and then we go to the snorkeling together, and then that's it's like he got a very nice motivation to come back. And now he is here. So I think I made a very good contribution to the OIST. Thank you. Anyway, and so like I'm very happy to hand over to the Pedro to talking about his research. Thank you so much.
Thank you. I have this one. I don't know if I need that one. Yes, if you need to snorkeling recommendations, talk to him. He knows a very good place. All right. So I'm going to talk about integrating interactive devices with the body. I think it really glues well with the topic of human augmentation and the whole exploration of this workshop. And yes, I come from the University of Chicago. That's where I do my research. That's where my lab is located, and I'm a professor of computer science there. So before this gets too abstract, I just want to show one example of what I mean with a device that is integrated with the body, just so you get an idea of what kind of integration I'm talking about. It's a very specific type of integration. So before this gets too abstract, I wanted to start with this example here. What you see here is 2 car designers. They're doing what car designers like to do, draw cars and figure out which shape is the most aerodynamic, which one flows best with the wind. Except normal car designers would stop here, and then they would switch to a computer simulator to compute the wind flow dynamics. But these folks are actually going to continue to figure out the computational airflow of the car on pen and paper. So this from here on starts to be a little unlike the systems that you might have, like an iPad or your computer screen, because it seems like this user actually knows the result of the simulation, and they're plotting these lines, these called streamlines, which is how the wind flows to the shape of that car. And in reality, of course, the user does not know the output of the wind simulator. That's why they use a simulator, because they don't know. These things are actually not super intuitive. What's actually happening is that this user is connected to a muscle stimulator. You see these little electrodes here? They're sending tiny electrical impulses to their muscles and causing their muscles to move so as to plot the result of the simulator on pen and paper. So for a second, the user cedes control of their own arm to a little computer that is in the background that starts to control their arm for them and plots. And I'm not going to play the rest of the video, but it's a really long video. It's about 10 minutes long, where these 2 car designers continue to use this system very fast, very intuitively, like it's part of their own body. And that's what I mean with a system that is integrated into the body. This muscle stimulator is becoming the display. Without that muscle stimulator, there would be no output, there would be no display, and they couldn't understand what's happening with the interface. And so the reason why I'm doing this, I'm hoping you're thinking like, why did the University of Chicago hire computer scientists to put electrodes onto people, is because I'm starting to see a really interesting trend line when you take a step back and look at the history of computer interfaces. And maybe many of you were even privileged enough to play around with the first early computers when universities only had one computer. OIST is too recent as a university to be in the mainframe era, but universities that are older would have one single computer, and all the users would fight to use that computer, and computers were ginormous, and even the interface would take up a whole wall to just control and put a program and get a program back the next morning when your computation was ended. What I'm going to try to tell you here is that every time that human-computer interaction people stepped into this game and made a new interface, a new way to access a computer, new things became possible that were not possible before. So about in the 60s, 70s, and 80s, there was this big revolution in interfaces called the desktop interface. This was the first time that you didn't have to sit in front of a wall or even go back home and come the next day to observe the output of a computer. You could kind of have a dialogue with a computer in real time. You would click on something, the computer would show you visuals back, and it was almost at human speed. And that ability to have a dialogue with a computer at human speed rather than wait overnight to get the result of your computation made this whole revolution of, word publishing and, video editing became computer video editing. And of course, newspapers became all edited on computers. The whole world changed just because the interface changed. And so what I'm starting to notice is that every time the interface changes, the whole world kind of follows and new things are possible. I definitely remember the first time I used Google Maps. It was on my old computer in the basement of my parents' room, and I was very confused why this would be interesting. I'm here in the basement. Why do I need to look at the map? But if you're anywhere, anytime, right, with your phone, which is, by the way, the computer that exists the most, there's more phones in the world than people. It's kind of scary. In the 90s, these things started to exist, and the computer moved into our pockets, so it can go with us. We can access it sort of in a handheld form factor. We can look at it and so forth. So Google Maps makes a lot of sense if you're walking around. And you gotta get the idea where I'm going with this one next. There's another revolution. I see lots of you with wearable devices like the Apple smartwatch and so forth. It is interesting and very different when the computer stops being a bubble that is small, mobile phone, and detached from you, and now physically makes contact with your skin, right? Acts as an interface to your skin. That's what wearable devices are. And no wonder that the things that most of you do with your wearable devices are things like step counting, because it's with you 24/7. Some of you might do the sleep monitoring, right? What's the quality of my sleep? Some of you do heart rate and other physiological data. That's literally because it's touching your skin. Otherwise, there's no way your phone from the vantage point of your pocket could do that. And so my research question, what my lab works on, is trying to figure out what happens next. So if there's another revolution next, new things will become possible again. And so there's two parts of this talk. One is maybe you buying the revolution that I'm about to say that happens next, which I'm sure you've already understood what it is. It's that the bubble goes inside, but also examining what new things might be possible once that bubble, the device and the user integrate and goes inside. And so that's what I mean with integrated with the body. And that's what this talk literally is about. And I said that one example was that device, just to illustrate how, of course, if I take the stimulator out, there's no interaction, there's no more device. So it's really integral part, the stimulator, the user's muscles. Without the muscles, the device also doesn't work. It's a very weird kind of display because your iPad works regardless if you're there or not. This one only works if your muscles are there. So you're part of the device too. So you're gonna see a lot of devices that are very extreme, but they were purposefully designed to be extreme. So to show you what would happen if parts of the user's biology get integrated into the computer device. All right, so let's start this. And there's sort of two main tracks to my own research work and the work of my lab. And the first one, you can already see there's a lot of virtual reality in these little thumbnail pictures. And that's because what we're trying to figure out, and Kurita did a great introduction to the need for haptics, the need for forces, the need for tactile sensations. I'm sure many of you have tried virtual reality by now and you're impressed by what you can see in VR. This is actually not even a game you buy. This is something my student Jazz made in a few hours. And you put your head in there, you look at this desert, feels very immersive. What you see is kind of almost what your eyes would see if you were walking around the desert, the same for the snowy mountain. But all of you know that it's easy to break these illusions and make the virtual reality feel unreal. And one thing that many of my participants do in the studies when I ask them, how do you know this is not real, is that they just try to touch something. And they say, like, I try to push against the wall of this shed and there's no force, there's nothing there. The illusion breaks, and very rapidly, they also start to see, well, actually, this is very pixelated and this and that and that and that. But it is through the body exploration that they very rapidly find out they're in a virtual reality. And so, of course, there is a big push, and you saw that a little bit with Kurita Sensei's work too, by creating more force feedback haptic devices to create physical sensations so that you could actually feel like something is there. And in fact, if you roll back the history of robotics, just a couple of decades, back to the 90s, you find the exoskeletons that he mentioned, devices, really beautiful devices that put a motorized joint at every joint of your body, and through that motorized joint, they can push against you. So what you see here is called ExoEL7. It's a very nice device. I like this one a lot. This person is rolling this ball virtually up and down the incline, and they feel the motor gearing against their own body, simulating gravity. So it's like a ball that's actually rolling back and has some weight. Now, this is a really cool device, but none of you have this at home. And maybe some of you have a virtual reality headset. And the reality is because these two things just don't mesh very well. This is the headset that you can buy like 5 years ago. My talk is so out of date. You can already buy the V3 of each of these. You just walk into a shop, you buy everything in the headset has evolved in terms of engineering and in terms of interface to be very portable, untethered. There's no cable sticking out. The tracking is called inside out. There's no more things you have to instrument in the room. I never thought I would even see that. And it was so fast that we arrived at that. And the whole interfaces are super mobile. And yet, if we wanted to have haptics and realistic forces, we would have to be tethered to the wall, right, with this gigantic device. It's so heavy that it's actually being held up so the user doesn't have to lift it, which is why the Sensei works on soft versions of this, also very exciting. But for this to provide a force, it has to use a counterforce, right? Newton's third law, so it has to push against the wall so it can push against you. And this thing needs so much battery that the batteries are not even here. It's tethered to the power, right? So this thing just doesn't flow with the idea of virtual reality as we have. It doesn't flow with the idea that we've went from mobile to wearable and things are getting smaller and smaller. This would be stopping, reversing the flow and almost going back to the mainframe computers, and we have to be in one room to experience VR. And that's not what we want to do. And so in my work, I've been trying to find ways to use the user's muscles instead of using motors, right? And so you're kind of getting the idea of what I'm proposing here. I'm proposing a shift to the muscle stimulation because we already have tiny motors in our body. They're called the muscles, right? If you're not familiar with the technique of electrical muscle stimulation, this is long history. This is borrowed from medical rehabilitation and neuroscience. We obviously did not invent this. This is back from the 60s, and it's typically used for rehabilitation purposes. Here, I'm doing something slightly different. I'm putting a computer, in this case, it's this wearable device over here, like this small electronics. I'm putting this computer in charge of the muscle stimulation. It talks to the virtual reality, gets information. I should stimulate the muscles in this manner, and it does it. It's not your doctor dialing the knobs. It's just a real-time computing system doing the job. And again, if you're not familiar with muscle stimulation, what happens is that you apply a small electrical impulse. For example, in this case, if you would do it on these two top electrodes, on the top ones, these ones, your arm would involuntarily, without you having to think about it, just move upwards. Okay, so that's what happens in the presence of electricity. The muscle fibers contract. And so if you put this together with what you saw earlier, you can kind of attempt to give to the virtual reality this sense of physical boundaries, maybe even a sense of mass, a sense of weight by adding the muscle stimulation. So this is work I did with my former advisor, Patrick Bodish, when I was a PhD student at HPI. And so what you see here is a user in VR, except this virtual reality is unlike the ones you might have tried. This one actually has physical boundaries. He cannot penetrate in the walls because his hands repel with the muscle stimulation anytime he touches one of those walls. And similarly, and I'm going to cut a little bit in the video here and jump some seconds, he's going to enter this final room where there's a cube, and he grabs the cube. He feels his hand snap to the cube and sort of stop, cannot collapse because there's boundaries to the cube. And again, that's the muscle stimulation sort of moving his hands outwards. But even when he grabs the cube, he feels a sense of weight because his hands would automatically fall down with the muscle stimulation. He has to fight up. And that juxtaposition of force is one pushing down involuntary, the muscle stimulation. You voluntarily pushing up. When you ask people, how does it feel like? They report, this feels like weight. This feels like the cube wants to fall down and I want to push the cube up. Feels literally like it has some weight, some gravity to it. Now, what's most interesting, and I'm very happy in the Q&A, talk about the limitations of this stuff. We haven't fully understood how to accurately control muscles, and you'll see that in some of the demos later. But ignoring that for a second, once you juxtapose these two approaches, you can kind of see why I'm excited about this one. It is incredibly small, and I'll show you that we can make this even small later. So if you can only remember one slide from my talk, it would be this one. That what I'm trying to do in my lab is that instead of adding more electronics to the body, which is this, to externally induce sensations, I want to create a force, therefore I'm going to find a motor and put a motor on a person. What I'm going to actually attempt to do is to find what is the minimum set of components I need to add to leverage the internal mechanisms the person has, the biology, in this case, their muscles, to create the sensation. In this case, it's force. So I can do force with muscles instead of force with big motors, big heavy motors. And you'll see this being echoed more and more in the talk as we go through. This is not going to be a very technical talk, but I just wanted for once to show what's inside of one of these devices so you get a sense of what's actually inside. And so this is one that I did. I'm not even showing what this one does, but they're all kind of the same. They all have a microcontroller. This one has some wireless or Bluetooth to talk to the virtual reality. So the virtual reality says, hey, create a force here because they're touching the wall. And that's how the communication gets there. And at the core, this is the most important part. It has the same type of stimulator that the doctors use for medical rehabilitation. You know, in this case, it's a medical grade muscle stimulator, except instead of a person controlling it with little knobs, we have a digital circuit that controls the current, that controls the voltage of that stimulator, so it behaves accordingly to what the virtual reality simulation wants to do with it. There's some batteries, and then the last part is the electrodes. These are the sticky pads that connect your muscles. Now, if you're a bit of an engineering mindset person, you're probably already suspecting what the next slide is, which is that this stuff, this solid state electronics, is the same stuff that is inside your phone. It means this can be made as small as you want. There's nothing here that is a mechanical moving part. And so when you don't have that, you can miniaturize things very heavily. That's why your computers keep getting smaller and smaller and smaller, because there's nothing mechanical inside of computers. And in fact, just to illustrate, this whole circuit, I was a very bad engineer when I was a PhD student. I'm a computer scientist, not an engineer. My students in my former postdoc, June, who's actually been here at OIST for a while, they made it really, really small. They made it so small that we can put it in someone's nose. And obviously, it's exactly the same device, by the way. I'm happy to show you why you would put a stimulator, electrical stimulator in the nose. But this is just to illustrate size. And this has Wi-Fi, battery, stimulator, electrodes, everything. The only thing you cannot miniaturize is the electrodes, as they need to be respectively large to fit whatever muscle group you're talking to. If you're talking to the biceps, that's a large muscle, make it bicep size. Obviously in the nose, it's a small nerve in your nose, and so we can make it fairly small. But just to tell you, that's the advantage of dealing with non-mechanical systems. You can make it really, really small. Just transistors, they go really small. And so again, once you have something new, once we've instantiated a new paradigm for human-computer interaction, one of those new revolutions of computing, then you can ask the question, what new things could we do with it that are impossible to do with the previous generation of devices, right? What things can this do that your smartwatch cannot do? And one of the things it can do is it can create mechanical forces. Your smartwatch is so tiny and is non-mechanical. It can't move your hand to a particular location or show you a body pose or draw your attention to an item in the environment. And so with these things, we can do lots of that. I'm just selecting one demo for my student Udai to illustrate this. This is a demo where you see a participant here. Oh, this is actually Udai. You see Udai here going through a training simulation in augmented reality. I don't know if at OIST you guys have to do fire safety training, but we have to do that every year or two at U Chicago. And the reality is people do it, and in the real fire, which happens often in my lab because we have laser cutters and all kinds of, nobody remembers what to do, and they're just struggling. Because there's no visceral sense of what your body needs to actually do to reach the fire extinguisher or to go to the emergency door or when not to do things and so forth. And so he's doing a virtual reality simulation here, or sorry, I should say augmented reality fire training. So the fire is virtualized, but the environment is real. This is my lab. But he forgets the next step, which is to locate the fire extinguisher. He doesn't know where it is. But he's wearing these electrodes on his neck muscles. And so the system automatically moves his viewpoint to look at the fire extinguisher by electrically stimulating his muscles down to look at the fire extinguisher. And that's how he locates it. And again, all the videos are on YouTube. The rest of the video is kind of fun because he'll try to put out the fire, he'll fail, and then the system will show him the exit route, how to leave the room safely, because that's actually really hard to memorize. And if there's smoke, it's even harder. Again, what I'm trying to illustrate is not that we're the first people to have the idea of moving the neck. Again, people in robotics and rehabilitation devices have done the same thing. It's just that these devices, because they're mechanical, they end up covering a really, really large space, right? Imagine going to OIST to work with this worn on versus with a device that doesn't even need to go above the neckline, and it's all kind of a membrane and soft. These electrodes are very soft and flexible, so you can kind of make them into fabrics in any shapes you like. It's a good problem to have, that the electrodes are really the only limitation we have. All right, so I'm going to kind of close the chapter here on the force feedback and put you in the shoes where I was when I started my lab at the University of Chicago in 2019, which was, we knew we could do this idea of integration for muscles. Okay, we can take out the motors and put the electrodes and we get forces. But can we do this for other senses? We're going to talk a lot about other senses in this workshop. People will talk about temperature, people will talk about touch, people will talk about taste. Can we do the same thing? Can we take out a mechanical actuator and put something that talks to the biology? And so that's what I'm going to show you first at the example of temperature. So we're going to return back to these two examples. And if you look at these virtual reality simulations, imagine that you were actually training to be in a desert or in Okinawa's, heavy kind of hot sun. You would only feel like you're in Okinawa if it was 30 degrees and really, really hot. So again, if you put someone in this VR desert and ask them, is this realistic? They might say, what I see is realistic, but not what I feel. It doesn't feel hot. And that's normally how a desert feels like, or of course, a mountain, conversely, should feel kind of cold. So temperature is really critical. And researchers in my field, what they often do to make really exciting simulations for whatever purpose there is, training simulations and so forth, when they require temperature, they really put air-conditioned units and heat lamps and other things that really heat up the molecules in the air around you. So of course, these things feel hyper-realistic. I've done exactly the demo you see here. I was mind blown that I felt like I was in a hot environment. Now, of course, this is not going to work with the headset that you buy and just walk out of the shop with it, because this thing takes 1 kilowatt of power to run for a few minutes, and the headset would drain out the battery in 10 seconds if you would use a kilowatt power device. So again, the idea here is how can we make this more portable and more congruent with the evolution of mobile, wearable, integrated. And so what you see here is work from my student Jazz. First year he joined my lab. And what you see is a person heating up their hands in a virtual reality simulation. The temperatures, of course, imaginary, is virtual, is not there. But notice that she's not wearing any temperature-like device. She's actually wearing a device kind of at her nose, pointed to her nose. So what's actually happening is that this is a smell device. All this can do is pulverize, atomize a few droplets of a solution that we put here. This is an ultrasound emitter, and pulverizes something. I mean, this is just so you guys can see it, because the droplets are so tiny, you can't see anything, but you can inhale those droplets. Now, the key to understanding this is, why would one target the nose if we're trying to create temperature sensations? And so you can look at the nose, and you can look at the nerves in your skin as well for clues of what my Jazz and I were thinking when we did this, which is the skin nerves and the nose nerves, especially sensitive, but the skin nerves do this too, are sensitive, of course, to temperatures, meaning there's cells inside. When it's very hot, they fire and tell your brain it's very hot. When it's very cold, they fire and tell your brain it's very cold. But some very interesting evolutionary reasons, perhaps, they're also sensitive to chemical stimulation. And all of you have tried this before, because you've eaten maybe Indian spicy food or any food with capsaicin, which is the main ingredient in chili peppers, and you felt very hot. And the individual nerves that were targeted by the chemical stimulation, they had no idea it was thermal or chemical. They were just firing and telling your brain it's hot. Obviously, contextually, you're eating food with your friends and you realize, well, this must be the capsaicin that's happening. But if you are in VR and you're inhaling a microliter divided by, I don't know, 100 maybe, because you have to see how many puffs we do, but it's a microliter diluted in capsaicin, then it starts to heat up the inside of your nostrils and you start to feel really hot. So that's what's happening to her. She's inhaling capsaicin. That creates this hot sensation about 10, 15 seconds. And then the wind comes, blows the door of the cabin open, fire goes out, and we do the opposite. We start to emit a microliter of eucalyptal. And if you ever had a breath mint, and I should have had one before this talk, but these kinds of things, they often have laced with menthol or eucalyptal. That triggers the opposite nerve. These are the trigeminal nerves, by the way. And this eucalyptal creates the cooling sensation. And now she goes out and there's snow, and we project the eucalyptal more and more often. She feels colder and colder. This one is much faster than capsaicin, so about 5 seconds maybe. And at some point, she finds the backup power generator, turns it on, etc. I won't play the rest of the video, but you get the idea. The idea is that there was no real temperature changing. This was just an illusion of temperature. And we can do it very cheaply, because all you need to do is turn on one of these tiny atomizers and pulverize a solution, versus actually, turning on a heat lamp and heating up a filament or whatever technique you're using to heat up the air around. It's completely different power schemas. Obviously, this is not as powerful as this. I'm happy to talk about some of the limitations we found too. Surprisingly, people tend to report this as a full body sensation, although obviously it should be more localized to the head, but they tend to imagine the temperature sensation happening in the whole body. And again, you're starting to see the parallel to what I said before, doing the same thing here, but for heat. I'm trying to find what's the minimum set of things that I can need to put on your body to make your body think it's hot or cold. And one option is a tiny bit of chemical and a device that digitally atomizes that. We can do this whole chemical thing on the whole body as well, because the skin has these trigeminal nerves, has these so-called TRP receptors or TRP receptors. So we can do cooling as well. Here you see Jasmine, my student, she did this work, and you can see her doing cooling on the cheeks. Okay, so there's, in this device, there's a silicone patch, sort of microfluidics type patch. You move the solution inside of the patch, but the patch is open to the skin. So your skin slowly absorbs whatever the chemical that is flowing through the fluidics channel. In that case, cooling. In this case, we can do the warming, again, capsaicin. Actually, there we switch to menthol because it's even more strong cold than the previous eucalyptol. We can do numbing, which is really interesting. This is topical lidocaine, so it's not as powerful as the stuff you've experienced at the dentist. But if you sort of self-touch, you're like, oh, feels numb and sort of generic. What's going on? And that happens about a few minutes after applying this topical lidocaine, 5% lidocaine. And you can do things that even mechanically would be quite dangerous to do. So this is actually a simulation where you learn what to do in a chemical lab if there's a spill of some kind and you need to, oh, I need to wash my eyes and then do this, do that. And you can sort of feel this stinging, painful sensation that otherwise mechanically would have to sort of create a pinching machine to instantiate. We've done that in the lab. It's painful. But here you can just apply a safe amount of cinnamaldehyde. This is the same thing, the main chemical ingredient, cinnamon, in the cinnamon bark tree, and that creates like a stinging sensation. It's a very exciting haptic sensation. It's unlike most things I've tried in haptics. And again, same thing here. We're looking for the minimum set of components to kind of instantiate these haptic sensations instead of having to add one specialized mechanical actuator for stinging, and one for this and one for that. We just switch the chemical, and all of a sudden it becomes a new device. Switches from heat to a pinching device or to a vibration device by just switching a chemical, which is quite interesting. All right. So far, I kind of lied to you guys in a way, which was I said, oh, let's look at the integrated devices. But then all of a sudden, this became a talk about only output devices, only things that talk to the user's body, specifically haptics. So what I want to attempt in the second half of the talk is to kind of close this loop and talk about systems that would really be very different from our wearables, and not just like, this one is more like another wearable that you wear, and then in VR, it gives you sensations. But what if it's the whole computer is happening through your body? Is there any kind of meaningful information access I could do if my movements were a way to compute and access information and receive information back? And so I'm going to jump some of my earlier projects, but I'm happy to return if you have questions about those, and kind of jump into what people tend to ask me most questions about, which is, can you make someone play the piano? And the answer is, we're trying. But it is very interesting to imagine if learning a new physical skill was computer assisted. Computers have done real wonders at helping us learn cognitive skills. Like I open slides and I study and et cetera with the computer, and I run simulations, et cetera. When it comes to physical skills, the best you can do is watch a video, but it's extremely hard to translate the third person experience of seeing someone juggle. It's in the third person, you're, oh, what's going on? Maybe slow down frame by frame. Okay, that's helpful. But where should my muscles be? How fast should they move? Which finger should move when? And that's what we're trying to do here by plugging this whole system now back into a computer. And so what you see here is a project by, at the time, my intern, then my postdoc, and now he just finished and is joining University of Tokyo as a professor, Akifumi Takahashi. And what you see here is a person learning the James Bond song by just feeling their muscles being moved rather than by actively moving them. And the big part of this project was to just achieve this independent finger motion, because what you saw in my VR one or in that plotter one was an independent finger motion. It was wrist motion, sort of coarse wrist motion. So here the challenge was, where do you place the electrodes and how do you set up the computer system so that you can kind of have this 4 fingers, I must say, because the thumb is another challenge we haven't figured out very well, independent finger motion. And now with this, you can indeed start running the studies and asking, and we are running a study right now, longitudinally, to ask in 10 days how much people absorb from this approach. And it seems to be better than actually watching a video. So I'm very excited, but so far, preliminary data that Sia, one of my students, is collecting. Now, That being said, while we were able to achieve this independent finger motion, it's still fairly limited. I don't know if you guys spotted. I might play the video again. But if you're a pianist, you of course spotted it. It's only one joint that is moving. It's this one. It's called the MCP joint. It's not like a very articulated movement, right? And so it's easy to start the movement. It's very hard to stop the movement as well. Who's actually stopping the movement is the piano key that is there and breaks the movement. So we only start the movement. We don't even stop it. Because once you actually try to stop a muscle from moving with muscle stimulation, you get into this whole dynamics of control loops, which is a nightmare, and then muscles are complex. So what you saw at the beginning with the plotter, sometimes people ask me, can this fake signatures? And my answer is no, look at the data. So these are participants that we brought in to do that plotter demo that you saw at the beginning with the wind tunnels. They are, of course, unaware of what the actual drawings the computer is going to do. They just hold their arm there and relax and let it do it. And you can see that it actually follows the frequency of the signal quite well. And the error is about 2 millimeters on average, or maybe a little bit more, 4 millimeters, I forget. But it's not about the magnitude of the error that concerns me, is the fact that we can't stop on the target. In fact, you can see when there's a flat line, it just wiggles around, right? For those who are into control systems, it's called an oscillation, right? So can't get rid of the oscillations because stopping is harder than moving. And so one of the approaches we're doing here is to merge the muscle stimulation with mechanical systems, but use mechanical systems that are extremely, extremely small and low powered, so they are not taking up the whole space of the exoskeleton. So what you're going to see in this demo looks more impressive than the piano demo. This is Romain. This is work that Romain did together with Chenny Wan as well, two of my PhD students. And this was actually a demo he did at a conference where people could control which guitar note he was going to play. They would just select, I want you to play an E minor, and his hand involuntarily forms the E minor, and he just has to strum along. So this is involuntary. And not only it forms the chord, but he has to stop at particular finger positions to stop the chord. And so the key is that there's not only the muscle stimulation, but there's this tiny mechanical breaks. They stop the finger from moving when the finger hits the right spot. So we don't have to do the stopping with muscle stimulation. And I'll show you another demo of this, which is I find even more exciting. This is Yujie, one of my former students, talking to Romain, and she's talking in sign language, which Romain doesn't know. She's going to ask Romain, what's your major in sign language? And Romain is using an application on the phone to translate that. Again, he's wearing the mechanical brakes on his fingers and the muscle stimulation on his arm. So she asks, what's your major? He uses the phone to translate, and he responds back, human-computer integration, HCI, but in text, because he doesn't know how to spell HCI. He sends that to the glove, and the glove is going to attempt to finger spell in American Sign Language HCI. But again, instead of stopping with muscle stimulation, the glove is kind of cheating and only selects the fingers that should move, so breaks all the others, stops them from moving. And once a finger reaches the final position, just turns on the brake and turns off the muscle stimulation. So you're going to see the letters coming out now. Oh, no, sorry, I wanted to highlight the locks. The locks are just, couldn't be simpler, just a pull and a ratchet mechanism that Chenny Wan designed. So this is an H. That's a C, not too bad. And the I is a little bit harder. Comes out okay. If you speak sign language, you know there's so much more we can't do, like the whole positioning of the hand and in the face and etc. But this is already a very simple demonstration of someone that has no idea about sign language, and all of a sudden their hand automatically is augmented to create sign language output out of their body. So I think you're also hoping to, or I'm hoping that you can see where I'm going with the second trajectory, which is people know how to move their fingers. They just don't know the melody of the piano. So we can augment that and extend and teach them the particular melody. Well, they maybe know how to play, to move their fingers, but they don't know how to play the guitar. We can help and extend that. But what happens if we would completely go to a territory where we're trying to give you ability that you don't even have natively, that your body does not access? Moving fingers is just giving you the next cue. But what if it's something that you don't have at all? And so this is where I kind of enter the work that I've done with Shinichi, actually, and how I met him was through this project, in fact. So here's the thing that Jun Nishida, my former postdoc, but he did this work with Shinichi before he came to my lab. This is the thing that they figured out. This is a very, very clever system. If you've ever been to the doctor and they were worried about your neurological reflexes, they might have done this test to you. It's called a pen drop test. They drop a pen You try to catch it as fast as possible. If you're too slow, there might be something wrong with you. Shinichi and Jun said, well, we know how to cheat this test very well. We know how to accelerate you so that you'll never get in trouble with the doctor again, which is they can detect when the pen gets released. And they did it very nicely by tracking the person who's releasing the pen. And we can use muscle stimulation to accelerate your reaction time. So fast that, of course, you catch the pen. Look at how fast the person caught the pen. The pen even like slipped down. It was immediate, right? And so, with this, you can actually receive an award by the Guinness Book of World Records. So if you buy the book, this stuff is in there. I'm not joking. It's kind of crazy. You open the book and there's what do they call it? They call it something really weird, like the fastest human-assisted reaction time. And it's 50 milliseconds, which if you know anything about reaction time, it just makes no sense. 50 milliseconds is, your eyes haven't even seen something in 50 milliseconds and your muscles are already moving. But you're probably already thinking like, wait a second, Pedro, let's watch the rest of the video. Like, is the participant feeling cool about this or something is going on? And you're right? The participants, often if you speed them up by this much so that they catch the pen that fast in 50 milliseconds, the whole thing, this is what they say. They're like, well, it was a lot of fun. And they actually did a demo at SIGGRAPH for this. It's a lot of fun, but I'm not sure if I did it. Maybe I was coerced doing it. Maybe the system pushed me into it. What's going on here? And so to try to understand where these 50 milliseconds and the sense of agency interact and where they might lead to I did it or the system just did it for me, we actually started feeling that there were new research questions coming from the idea of computers and humans being integrated so deeply that these things like agency become dramatic research questions, right? Like with your wearable device, there's a very clear sense of agency. Either you touch it to do something or that's it. You know when you instructed it to do something or it vibrates and it wants something from you. Over here, the boundaries are kind of interesting and there's lots of philosophical implications to this as well. I'm happy to talk about that later. But just immediately you can ask, does the user feel motivated in this task if they don't have a sense of agency? And Kurita was even mentioning how important motivation is for people to continue training for their tasks, right? And so this became a whole research track actually in my lab, understanding the sense of agency with these integrated or heavily integrated devices like the muscle devices. I want to show you a lot of the stuff. We've collaborated with some neuroscientists doing experiments in fMRI. We've done artwork, but more importantly, this track here where we're kind of attempting to solve this problem of can we speed someone up and yet motivate them enough, give them a part of a sense of agency, some feeling like they can do it. All right, so I'm gonna jump, oops, sorry, I don't know why that's jumping around. I'm jump into that speed up stuff over there. So we're here, person is saying no sense of agency. And here's what we were thinking at the time. They're saying no sense of agency because the y-axis is their sense of agency, low means nothing, you did it for me. Up there would mean I did it, right? But reaction time over here, so that would mean I'm trying to catch the pen, I have maximum sense of agency, I know I tried, but I'm not fast enough. You could even imagine plotting, this is very easy to find, finding each of your fastest reaction time possible, you just do it 30 times and we average that out, or even take the minimum if you want to be on the safe side. And now we know 250 milliseconds or 300, that's the sort of normal for a normal population. And you can imagine that if we do that super fast 50 milliseconds thing, this is what happens. People say, hey, it wasn't me, it was fully assisted. I didn't even have time to see the thing falling and it's already happening. So too fast, no sense of agency. And then what Junichi, Jun, and I were starting to wonder is what happens if we delay the assistance? So it's closer and closer and closer and closer to your own reaction time. And we were honest, we didn't know, and even ourselves were thinking, maybe it stays like this. Our brain must be so powerful that it stays a step curve, like a step function. Like no agency, no agency. If we feel ever there was something there, we say no. It cannot be me because I felt something. I know my own body. I know the body schema. I know whatever the thing, the physiological thing you're holding on to. But that's not exactly what we found. There's a lot of flexibility in how our brain operates. So I won't bother you too much with exactly how we transform the pen dropping into something more stable, but it involves a device and reacting time to the on cursor changing visually, and they report a sense of agency. And every time they're being assisted by muscle stimulation. So we're speeding up their reaction time by different factors. And what you can start to see once you average everyone's curves out, because there's some participants that are more susceptible to this than others, but everybody seems to be, is that it's more like this gradual thing here. Of course, it's sharp, because if it's too early, you immediately feel like something is off. But if you let your eyes see it, if you let your motor part think about, I'm going to move, then we can cut off and speed quite a little bit of here, and your brain won't even notice. And in fact, there's a part of this curve over there where you can speed up by a tiny bit, and there's lots of points over there, the 7s. People were like, yeah, I did it. And these are already quite sped up curves. So they're being sped up, and they don't notice. But interestingly, and this was Shunichi and I making something up on the spot, we said there was some interesting point at the 50-50 mark. And we don't know why we got obsessed by the 50-50, but we said, wouldn't it be interesting if we could trade off agency and speed? Like a person says, oh, I want to be faster at the excavator that Rita was showing, but I still want to retain some motivation. I want the system to do it for me, but only 50% faster, because I want to still feel like in control. And at this paper in 2019, we made this up on the spot because we didn't know if this was important, this 50-50. But I'll show you that indeed it is. But just to give you some visuals of this person is being sped up. So there's the muscle stimulation kicking in 80 milliseconds before their own reaction time, and they still think they did it. And you can do all kinds of things with it. Now comes that part that I was telling you about, the training. So this is a really fun project that the three of us did again with some more collaborators, which was, what if we now train someone in a simple reaction time game, like if you were playing a video game and you have to hit the button really fast, mash the button as fast as you can when you have a visual cue. We're going to train them. We're going to first characterize how fast they are prior to our study. So they come one day, and Kazuma and others collect the data, and we know how fast you are. And then we're going to give you different types of training. And one of the trainings we're going to give you is that crazy super fast muscle stimulation, right? The one that ideally is showing you how fast your body could be, the Guinness Book type of fast. And then people try again. They take out the electrodes, and let's see how much they retained from that. How did they permanently become faster with that super fast Guinness Book of World Records? Not really. Let's delay the stimulation to that halfway point, which we kind of made up on the spot. But turns out it does help to retain the motivation. When they take out the electrodes, they're permanently a little bit faster by about 8 milliseconds or so. And again, 8 milliseconds sounds very small in everyday life, but if you're like playing baseball or whatever it is, I once did the calculation, and in 8 milliseconds, if the ball is pitched fast enough, it's the difference between the ball being here and already here. So it's gone. Right, so for reaction time type things, 8 milliseconds is a big improvement. It's a significant improvement. And remember, this is removing electrodes, throwing them out, which is another part that I wanted to talk about with this notion of heavily integrated devices. Is I'm hoping we can also design in this workshop and others devices that are not just working when they are there, but things that teach us new ways and we can take out, throw away, and now our body has acquired that skill permanently, because we have the architecture in our body to memorize these skills. The device just needs to be well designed to accommodate for that. All right, so as you can see, removal, and then they try again. All right, I'm gonna jump over the rest of the other sort of more agency type papers, but I just wanted to highlight one thing. This optimization of movement time and all this stuff to conserve agency is done when there's a very simplistic assumption, which is that you're trying to move to hit the button and the computer wants to hit the same button. I'm sure you are all thinking, oh, I can do all kinds of really interesting dystopian scenarios where the computer goes left and you want it to go right. And we have explored that. I invite you to read this paper. And of course, what you're imagining probably plays out, which is if the computer plays kind of an adversarial role to you, your agency drops really dramatically. Funny enough, if the computer gets stuff right that you got wrong, you tend to like want to own that outcome. And so people have a little bit of an artificial game of agency depending on the outcome, which we found kind of fun to observe. So they got it technically wrong, computer got it right. And they're like, yeah, 7, I did it. It was great. I was really good at this task. So I invite you to see that. But I wanted to say that there's all kinds of other explorations of agency one can do, like how do you turn on the device? How do you turn off the device? Not just assuming everything is aligned and working perfectly, but what happens if you want to turn it off? This is actually a really fun exploration for folks with EEG and et cetera. Like, can you predict someone's intention and turn on the device preemptively? Can you turn it off when they don't want assistance anymore? And so we've done that exploration in kind of very different manners. So in some of our projects, we just let the participants themselves design the gesture they want and have just a simple button that can turn on when they want to. So for example, in this project called Split Body, this person is writing an essay at the same time that she'll cook the soup using muscle stimulation. Sorry, not soup, she's making caramel. She's making caramel with muscle stimulation. She can turn it on and off. The stirring motion is automatic. And we found that, by the way, if you stir automatically, you can focus on this task better. You actually better outcomes on writing the essay or whatever task you're trying to do. So very simple, right? She splits the body, but she's always in control of the muscle stimulator by just pushing a button. So that's one way to control for the agents and always give control to the participant. You can do more interesting things. So for example, here's a positional control type of device. So this is an older project of mine where people would approach objects they don't know how to operate. In this case, a lot of people don't know that the first thing you have to do when you pick up a spray can is to shake it and not just try to spray it before shaking, because then just a lot of liquid comes out and no spray. And so when you grab this spray can, it starts shaking. However, if you're an expert user and you know that, you can dismiss the shaking, the involuntary shaking by the muscle stimulation, by just rapidly moving the device somewhere else. So it's positional control, okay? Here, the one that you saw at the beginning with the pen, I didn't tell you, but actually if you lift the pen, the muscle stimulation stops. So it's kind of like tool control. The tool and the muscle stimulation becomes sort of one on-off button. People really like that one, by the way. And you can even create more complex ones, like gestural control. So this system is moves to indicate where the YouTube video is at. So the play back position of the video. But if you do a crazy movement, like I was trying to catch that pen in the air, the system knows that movement has nothing to do with this and turns it off. So it's more contextual and more gestural. Okay, I'll skip the artworks. And just want to, for the last couple of minutes, highlight some of the things that are also interesting to do with this paradigm of integration, which is you can also solve some problems, some actual problems that people in the human-computer interaction and computer science had. I've shown you a little bit of our approach to solving the, how can big exoskeletons and very small portable VR merge together? Maybe it's through muscle stimulation. But there's another very pressing problem right now in my field, which is everybody wants to have tactile sensations. I want to touch the virtual world and feel like these little vibro motors in a glove, vibration motors, so I can feel the world. But they also want to be in augmented reality and fix real tools and engines. And so your hands must be free if you want to manipulate a real engine and be able to fix it. And so these things just don't go well together. Like if you ever tried to open the door of your house while wearing gloves and jiggling the keys, is almost impossible. Imagine like fixing an engine with a wrench. And so what we've been trying to do is solve that as well with also biological and neuroscience insights. So what you see here is a person in a virtual reality simulation. He's actually grabbing the rope. He's feeling the texture of the rope. His hands are entirely, the palmar side of his hands is entirely free. He's also feeling the virtual bolt. He's going to climb this bouldering thing. He's feeling the sensations on his hand. And yet again, how is he feeling something if there's nothing on his palm? Normally, if you want to create a tactile sensation, we put a little vibration motor on the palm. And the solution in this case is to do electrically, but to do it in strategic locations. So these electrodes are in places where the nerve that is going to go to your finger pad is just about before it kind of turns down. And so we stimulate the nerve, but it stimulates, your brain thinks it's stimulating the finger pad. So we're stimulating from the back, but the sensations are felt on the front. So the person feels highly immersive sensations without having to wear any of these gloves. These are all, by the way, products. So you can kind of imagine where the world is going in the next couple of years. It's going to be very exciting for VR, but everybody's going to be wearing gloves and having to take them out to just shake hands or to drink a cup of coffee or to type your password to unlock your computer, because with gloves, you can't do any of that stuff. That's a really big thread in the work in my lab. I won't talk much about it because I want to conclude. But if you want to learn more about how to create tactile sensations while keeping the area that you're targeting free, you can check out the work of my PhD student, Chen Yuan Tang, because that's his PhD topic. All right, so conclusions. Just want to give you a few takeaway messages, and then we should turn onto questions. I think we can think of these integrated devices as one of the next generations of computers. And what's really interesting is that they seem to fit the mold. They're becoming smaller and smaller, and they enable us to do one new thing. And that seems to me like valid paradigm. By leveraging the biological actuators, we tend to have something that is always smaller than the previous generation of mechanical devices. And you can kind of ask yourself the question, how far can you push this? And of course, many of you probably thinking about, what if you go to the brain? And indeed, you can push this even further by stimulating the brain instead of having to wear a full suit of vibration devices or whatever it is. So what you see here is a project that we published very recently. And this person is feeling tactile sensations there, he's feeling tactile sensations there in his hand. And it's because he's wearing a transcranial magnetic stimulator, so it's a type of brain stimulator that is non-invasive. And that can generate an impulse when he, for example, should feel like his hand recoils, as based on this projectile in VR leaving his hand. So what that's going to do is that stimulate the part where the brain normally represents the hand. And you feel like, whoa, somebody pushed my hand. And in the game, he continues to play that. Notice that the stimulator is now going to move to the other side. Now on the side of his foot, the brain is sort of opposite, right? The sides to the limbs. So now we stimulate and he feels like, whoa, there was a big impact in my foot, so forth, so forth. So you can kind of generate those sensations just from the brain. This is work from Yurai Tanaka. Again, what's interesting is that by doing so, you end up with these devices that leave some areas free. This is, by the way, this is work from Keigo, who's right there when he was my intern. Really, really cool that he's able to be here today. And then I wanted to also leave as takeaway message that I've shown you some examples of new abilities. There's so many more new abilities one can endow users with. This is another demo from their fast reaction time. This is a person trying to take a photo of a baseball flying past by. It's really, really hard because your visual reaction time is not fast enough. But of course, imagine you instrument the baseball cannon with a little sensor. You do muscle stimulation so that the person actually hits the shutter button on the camera, and this is what you can do. So as you can see, they took the photo. The ball is right there in the photo, and they thought they did it. And again, by doing this approach, you can also train people to be permanently faster. I just want to highlight that the other part that I find really interesting, and I think that's a glue that unites a lot of us in the workshop, especially those that are maybe not computer scientists, is that this is more than just talking about symbols. This is not computers just showing us text. This is computers really showing us bodily knowledge, tacit knowledge, things that are highly contextual, highly physical. And that's, I hope, something that we all value, and maybe we can create more systems like that. Here's another example of that split body system. The person can automate different parts of their body. Here he says automation goes to there. He focuses on playing the piano, but he can flip that. This is very useful for beginners because you can't do both at the same time yet. Now the synth is automatic. He can focus on playing the drums, and hopefully he's good enough. He takes out the electrodes and he plays both. We're also trying to figure out if that helps people. I'll skip over Jun's work, but you should check out Jun's work. Super cool, highly tested knowledge. This is passive devices, teacher and student connected. And then, of course, I talked a lot about nerve stimulation today, but this idea of integration, I think, is bigger than nerve stimulation or muscle stimulation or chemical stimulation. It's about really thinking of the computer system as another unit, as another entity. And in fact, I invite you to, I'm not going to show this in detail, but I invite you to check out a work that I did with my student Jasmine, where we integrated a physical living organism inside of a person's smartwatch. So they felt more connected because they had to take care of this slime mold every day. Otherwise, he would die and their smartwatch wouldn't work anymore, which was really fun. All right, just to close it up, I'm just voicing the work on behalf of these people. This is my team, and this is the people who really did the work. And so I'm just here representing, and I'm happy to take any questions. And thanks, Shinichi, Tom, and of course, Jonas, for organizing this and making this possible.